In this video, I'll be talking about the VBA script of SOR method, successive over relaxation. This is particularly useful for the problem 3 of homework 7. This is similar to example 8.6 and 8.7 of the textbook. So this is the SOR subroutine. We don't have any other function than this subroutine, so this is actually pretty straightforward to go through. We start with the declaration part. So here are the variables we have. M and N are the number of intervals along the X grid and along the Y grid. I have phi, which is now an array. dx, dy is del x and del y. U is basically the uij that we talked about in part 1. So I, j, k are indices. I have the SRF factor, phi old as double, maximum iteration. So these two are, we need to set these for stopping the iteration over the grid. So we get that, we get to that in a minute. All right, and then we also need a counter, which is I call the CNT. All right, so let's see how we can implement SOR and how we can modify the boundary condition to solve problem 3 of homework 7. All right, so as usual, we have to read the input variables from the spreadsheet. So we're going to read the n number of discretization along the x-axis, along the y-axis, del x and del y in successive relaxation factor from the spreadsheet. We're going to redimensionalize our phi now, since we know how many discrete points we have along the x and along the y. We can actually discretize it. So this is phi I m and m comma n. So here is the first tricky point. Because the first index indicates the row, by changing the first index, meaning that we're going to change the rows. Changing the rows means that we are moving along the y-axis. So the y-index shows up as the first index in VBA. That is different from the first index that we have in the note. So let's go over the note again. What we discussed in part 1 of SOR, I used phi ij indicating I as the index along the x-axis and j as an index along the y-axis. So j, which is index along the y-axis, shows up second, and y shows up as the first index. Okay, so x index shows first, y index shows second. This is what I have in the note. But when you get to the VBA script, you better have the opposite, because when you change the first index, means you're changing the rows. So in array, when you change the first index in VBA, that means you're changing the rows. Changing the rows, that means you're moving along the y direction. How can you change the row and not moving along the y-axis? All right, so think about that. So the first index indicates y-index. The second index, or the second variable, indicates the x-index. All right, so just to keep in mind. All right, how we can get del x and del y? Well, if I know that I have n discrete points along the x, then the increment would be 1 divided by 1 minus, or 1 less than the total number of grid points. Okay, I'm assuming that my box size is 1 on each side, 1 along the x-axis and 1 along the y-axis. Anyway, so del x del y is 1 over n minus 1. Don't make a mistake. This is not equal to 1 over n. Okay, the number of increments is always less, 1 less than the number of grid points. Okay, one more time. Number of intervals is 1 less than the number of grid points. And that's why we have n minus 1 downstairs and n minus 1 over here. Anyways, So after we redimensionalize our phi, we're gonna fill it up with our guess. Our guess initially is on the spreadsheet. So let's look at the spreadsheet that we have. Okay, so here's the spreadsheet that I prepared. And I have boundary condition zeros along the top, zeros on the east edge, zeros on the south edge, and 1 on the west edge. Okay, and these points are my intermediate points. All right, so let's start with some initial guess. I'm going to put zeros everywhere. Okay, so let's put maybe 0 here. So let me copy that and paste it over. So this is all zeros. I color coded because it looks nicer. Small number close to 0 are colored blue, and the maximum number, which is 1, are colored red. So you get a spectrum, you get a color range from blue to red. More blue means closer to 0, more red means close to 1. All right, now since we have all zeros around this part, I get all blue, and then 1 here, I get red. Okay, so we're going to read these values as the initial condition. All right, so we know that SOR needs an initial guess. So I'm going to go over all the columns I from 1 to n and all the rows from 1 to m and calculate, well, read the values to phi array. Okay, so these 4 or 5 lines are going to fill up my phi array. All right, now let's apply our SOR. So we know that we have to iterate over our iterative equation as long as the maximum error is greater than the tolerance. So initially we're going to set the counter, which is number of times we have swept, equal to 1 maximum error. Let's start with assume that maximum error is 1. So I'm going to have a while condition because I don't know how many times I have to sweep over the whole grid points. So this is where while loop is useful. In the while loop, I have a condition that my maximum error, as long as that is greater than my tolerance, which is 0.0001, all right, and number of iteration is less than 100. Suppose you put a very small iteration, you put a very small tolerance here, and then the maximum error doesn't reach there very quickly. So then you have to go over this many times, and maybe Excel freezes. So I suggest put another condition such that the number of iterations or number of counts or counter better be less than 100, or some medium range number. In that case, if the tolerance doesn't reach to that tolerance, and you go beyond this maximum number of iteration, then this condition actually becomes false. This whole thing becomes false, and then the while loop stops. Okay, so this doesn't let Excel freeze. Okay, so every time we're going to go over this loop, we're going to iterate. We're going to increase the counter by 1. We initially set the maximum error that we have here. This is maximum error old. I set it to 0 right after the while loop. I set it 1 because if I put 0 here, I do not come to the while loop, because I violate this condition. 0, if I put 0 here, then 0 is not greater than 0.0001, so this is false, and this is true. So when you add the two logical operation or logical statement, the overall result becomes false, and you never come to the while loop. So do not put 0 maximum error initially. Initially is 1. Once you enter, you make it 0. Okay, so then you have to sweep over all the grid points, the intermediate grid points, not the boundary points. And then you calculate phi u, basically is ruij. So let's go to the node. Uij was basically this expression, del x squared phi ij minus 1, blah, 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 all the way to the end, divided by 2 del x squared plus 2y squared. So I'm going to write this exactly in my script here. This is del y squared times phi ij minus 1i, j plus 1i, plus del x squared times ji minus 1 and ji plus 1. And the whole thing divided by 2 del x squared, 2 del y squared. So this is u. And then my phi would be the phi old, exactly what I said, times plus SRF times u minus phi old. So remember, when I was talking about this equation, I indicated that whatever is on the right is old. This is phi old, and that is u. What is on the right, what is on the left is new. So this is phi new, the other ones are phi old. And I have same thing in this script. So phi old on the right, and then phi new, just phi on the left. Okay, so then how do we define maximum error? The maximum error is the difference between phi new, which is phi ij or ji, and phi old. So we're going to calculate this maximum error for every grid point, and we're going to compare that with our maximum error old that we have before. If this current maximum error for the grid point is greater than that, then we're going to assign maximum error old to this new one. So the new value, if it's greater than old, we're going to keep that as old. Okay, so this is to just pick up the maximum error along the grid points. All right, so now we're going to sweep over I and j. So by this line, we're going to sweep over the whole grid once. Now, this is the time to check the maximum error old. If maximum error old is greater than this and the counter is less than that, we have to iterate one more time. Okay? So we're going to go over this again. We're going to go over all the grid points to calculate phi ij or phi ji, calculate the maximum error, compare it with maximum error old for every grid point. And if it's bigger than that, then we're going to pick up the bigger one. If it's smaller than that, we're going to keep the bigger one. So by the end of the while loop, we are sure that either the maximum error is less than this, or we've reached maximum number of iterations. If we reach maximum number of iterations, that means we couldn't actually hit the threshold. So that means there's something perhaps wrong, or convergence is slow. Oh, by the way, SRF is the factor, is the successive relaxation factor, which we got through input from the spreadsheet. Okay, so anyways, if the threshold is less than that and counter is also less than 100, then that's convergence. It comes out of the while loop. Either in any other circumstance, as maximum error bigger than this, or the iteration bigger than 100, then we're going to actually stop the while loop. That means the convergence haven't been reached. Okay? Anyway, so by the end of the while loop, either we converged, or if it didn't, the counter has to be bigger than 100. Or I'm sorry, the counter is a maximum 100. Okay? Well, if you put 1,000, then you actually iterate more. Hopefully, you get converged. All right, so after the while loop, we're going to print out number of iterations, which is actually the CNT variable. So this is, we're going to write this exactly as a text because I put it in quotation. So in cell row 1, column 7, you're going to see this text exactly. Okay, this is the number of iterations. In cell 1, column 9, we're going to print out this text, max error equals to. I'm going to write this text exactly onto that cell. And then the value of the maximum error will be printed out on column 10, which is right next to column 9. Anyway, so these are just the overall parameters that I kept in my script. And then finally, I'm going to print out all the Vij to spreadsheet. So we're going to go over all the cell array, all the phi array elements, and then going to print them out onto the spreadsheet cells. So this is the bottom of the code. I hope this is clear. Now, for the homework problem, you have to change the boundary condition. Well, initially, the boundary condition we had was 0 across the north side, south side, east side, and then 1 on the west side. In the homework problem, we have derivative, I guess, either on the north side or east side. So all you need to do is, after you calculate Vij, means right here, so you have to add the condition here to calculate the boundary points, and that is through final differencing, either backward difference or forward difference, depending on where you sit on the boundary. let's say if d phi dx is equal to 0 on this, you have to implement this equation, exactly this one. All right.